How lowering fuel rate drives the blast furnace productivity. So listen closely because most operators get this backward. Productivity is not a target you chase, it's a mathematical byproduct of your fuel rate. So we are diving into the efficiency paradigm. So looking at the title slide, you see a technical blueprint of the furnace with a massive blue arrow surging upward. This represents the 15% productivity jump achievable through a scientific optimization. By the end of this session, you will gain three specific deliverables. First, a master level understanding of the oxygen carbon gasification limit. The second, 3.5 kg leverage rule for the capacity forecasting. And third, the aerodynamic law of K factor that act as your ultimate production gatekeeper. So we are moving away from the brute force blowing and towards a regime where reduced pressure drop and enhanced reduction kinetics do the heavy lifting for us. So if you want to maximize tons per day, you must first master the kilojoule per ton. So to understand how this works, we have to look at the hard physics of the two-year level and what actually limits our speed. So coming to the production equation. So in the raceway, the physics are absolute. Look at the central graphic level, constant wind. At any given max blast volume, the furnace can only gasify a fixed amount of carbon, roughly 340 kg per ton of hot metal. Now follow the contrast between scenario A and B on the right. In scenario A, high fuel consumption means the burden descends slowly because the furnace is clogged with the carbon that need burning. Look at the scenario B. By lowering the carbon requirement per ton, that the same fixed oxygen supply allow the burden to descend significantly faster. The so what is simple. If you require less reductant to produce 1 ton of iron, your fixed oxygen supply will yield more ton of iron per hour. We are effectively decoupling production from wind volume by making every cubic meter of oxygen work twice as hard at the tuer. So this is not just theoretical, there is a specific mathematical multiplier we use to calculate this production surge. The 3.5 kg leverage rule. So this slide illustrates the scientific standard of the furnace capacity. On the scale you see a 3.5 kilogram weight on the left balancing a 1% production gain on the right. This is the leverage rule. For every 3.5 kilogram decrease in your total reductant rate, your production increased by exactly 1%. So look at the distribution here. Roughly 350 kilogram are gasified at the 2 years, 100 kilograms are consumed by direct reduction, and 50 kilogram are dissolved into hot metal. The operational impact is massive. If you save just 14 kilogram of your fuel rate through the better chemistry, you have just found a 4% increase in plant capacity without spending any money on equipment. So efficiency acts as a direct mathematical multiplier on your furnace physical volume. But to hit these numbers, we have to talk about the chemistry occurring in the thermal reserve zone. Achieving a 3.5 kilogram reduction requires us to shift the chemical workload away from the hearth. So shifting the burden, that is indirect versus direct reduction. So this is the heart of the metallurgical battle, indirect versus direct reduction. On the left in blue we have indirect reduction using CO gas in the upper furnace. It's exothermic. It saves it. On right in orange is the solution loss or direct reduction. This is highly endothermic, consuming a staggering 159 megajoule per kilomole of FeO. Look at the Oostite reduction graph on the right. As we move toward the bottom, we see carbon plus CO2 reaction. The goal is to maximize your eta CO, your gas utilization, to starve the direct reduction process. The so what factor, every unit of iron reduced by gas in the upper stack is a unit that doesn't have to be melted using expensive coke in the hearth. By shifting the body to indirect reduction, we protect the hearth thermal state and drive the fuel rate into basement. However, you can only achieve high gas utilization if the gas can actually reach the ore. The aerodynamic enabler is our permeability, way about which we are talking. So, as you can see, the permeability basically dictate gas efficiency chemistry, and chemistry is a servant to aerodynamics. So, on the left, restricted flow shows high K factors and orange zigzag arrows. This is a nightmare, unreduced ore reaching the cohesive zone because of poor contact. On the right, ideal flow shows uniform blue arrows with the optimized gas distribution and maximum gas to ore contact time. According to Bernoulli's and Ergun principle shown in the sidebar, your pressure drop strictly dictate your maximum wind volume. Since the ferrous burden account for over 80% of your gas resistance, permeability is your ultimate gatekeeper. If your burden is tight, your eta CO drop, your fuel rate spike and your production collapse. To maximize indirect reduction, you must ensure uniform, intimate contact between the gas and the burden through precise charging and fines control. This is the only way to keep the furnace open for high velocity operation. Now let's synthesize these thermodynamic and aerodynamic laws into a single operational playbook, the high productivity playbook. So coming to this slide where we conclude with the high productivity playbook. So look at these four gauges like the dashboard of a high performance engine. From a left to right, we maximize wind and oxygen to hit the delta P limit. We optimize burden distribution to ensure an ore free center. We push the hot blast temperature to the highest achievable value to naturally speed up descent, and we control top gas temperature to preserve drying capacity. So the synthesis box at the bottom says it all. We do not chase production directly. Instead, we manage the aerodynamics of the burden and the thermodynamics of gas reduction to force the fuel rate down. When you achieve a lower fuel rate combined with the maximum sustenance wind, you reach peak scientific productivity.